we spend a little bit of time talking about the other condensed phase, solids. So we know we've talked about this molecular depiction of our phases of matter, that gases, molecules are really far apart, they're not touching, free movement. Liquids, the molecules are touching each other and moving around, whereas solids are much more restricted. The molecules are all touching each other and they're wiggling and kind of jiggling around, but they're not really flowing around. Whereas our liquids and our gases, those molecules can flow, they can move. And so solids have an important property of rigidity, right? Solids have a shape and they will keep that shape. And that's a really important property because liquids and gases don't have it. So that is unique among solids, and we use that a lot of the time in order to build things. It's important that our houses have consistent shapes. So I want to talk a little bit about the properties of solids and what makes solids special. We know that solids are just defined by the fact the molecules are touching each other and not really moving a lot. And so from that, the first kind of level of classification of solids, the solid can be crystalline or amorphous. Both cases, the molecules are touching each other, but in crystalline solids, the molecules are arranged in a regular pattern. There is some sort of pattern or structure that the molecules regularly follow, a distance arrangement of molecules, whereas in amorphous, they're much more random. It's almost like you took a picture of a liquid and kind of froze it, took a snapshot of a liquid where the molecules are kind of jumbling around and then all of a sudden stick in place or are stuck all of a sudden. You will note there may be local order. This little chunk of the amorphous solid sure looks like the crystalline that's right next to it. But overall, that sort of ordering isn't long range. It's very localized. And so for a given molecular formula, say SiO2, silicon dioxide, you could have both crystalline and amorphous forms of that solid that purely come from how they are prepared, basically how they form, kind of this physical setting that you form those in. Crystalline silicon dioxide is called quartz. Amorphous silicon dioxide is called glass. I do want to note the word glass. You're used to using that word to specifically mean amorphous silicon dioxide. You'll also see the word glass used like lowercase g glass for any amorphous solid. So like a glass, you could have a lot of different types of glasses. But you'll note in both of these silicon dioxides, the local bonding is the same. Each silicon atom has 4 single bonds. They're in a tetrahedral geometry, so they have 109.5 bond angles. And each oxygen would have 2 bonds and 2 lone pairs, just like you'd kind of predict from Lewis structures of these things. The difference is entirely in the long-range ordering. In the case of quartz, they're in these kind of perfect, pretty hexagonal shapes. They're just kind of repeating over and over. It keeps going. That pattern repeats over and over again. Whereas whatever pattern there is in this sort of glass quickly dies off. You will note there's still kind of these like rings that are forming. So there's overall still a similar idea because the basic connections are the same. They're just a little kind of wonky. They're not as perfectly lined up in a long range order as the crystalline material is. When you take these and look at them kind of in the macroscopic scale, they will look different. So for example, crystalline SiO2, crystalline quartz, has a hexagonal shape. So these hexagonal atomic shapes or atomic arrangements show up in quartz crystals. You have these really clean crystals that are growing in, whoopsie, that can't see that, growing in kind of these hexagonal rods out from this base. Whereas when you take glass, this is natural glass, so this is obsidian from like lava, it breaks, and you're familiar with what glass breaks like, right? It's really sharp, it's really jagged, there's just kind of lines all over the place. There's just kind of these flat pieces that are forming. There's no real kind of atomic arrangement that can be reflected in the piece of glass. It just breaks, however, randomly. And if you're ever at the Houston Museum of Natural Science, Colin Hall of Gems has plenty of beautiful crystals, huge, beautiful crystals that have shapes that reflect. You can figure out how the atoms are arranged in the crystal. Are they hexagons? Are they cubes? So you can see that in the crystal just like you can for this piece of quartz. So I highly recommend it. It's very, 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 very cool. Plus it's also just ridiculously big gems. Now, functionally, when we talk about crystalline materials, most solids are going to be called polycrystalline, what we call polycrystalline. where you have lots of small crystals that are kind of jammed together in what are called grains. So if you've ever heard that, talking about the grain of like a gem. So this idea of like if you had like a piece of like a solid, like a chunk of solid that you could touch and see that is all just one perfect crystalline material, like front to back, the entire thing is a perfect crystal. That would be really, really hard to do. It'd be really hard to grow because everything has to happen perfectly, and that's hard to do in real life. We call those gems that are like crystalline like that, we call them flawless. So, you know, they would be perfect in that way. You're dealing with a lot more polycrystalline materials where there's crystals, like little small bits of crystals that are all kind of jammed together. So not everything you touch is going to be a perfect crystal, but you can get some pretty impressively large crystals under certain conditions. And polycrystalline materials still have a lot of the same behaviors because it's just kind of big chunks of crystal still. All right, so it's more kind of general, there are a couple ways that we kind of characterize or talk about solids. And there's three big kind of properties that we want to talk about. They are hardness, melting point, and conductivity. So hardness is like a word we use to talk about solids in like kind of our everyday life, but we're going to talk about a technical definition that is the tendency of a solid to scratch. It's not breaking of the solid. We'll get into that. But melting point is what we think the temperature of the phase change, right? What temperature do you need to heat up your solid till it melts? And conductivity is transmitting heat and electricity. So something that is conductive, a solid that is conductive, will transmit both of those. So conductors are material solids that conduct heat and electricity. Insulators do not conduct. So both of those are useful in their own kind of application. Sometimes you want conductive materials like the copper wiring in like running the electricity to your house, but insulators like the insulating foam around your house are also useful when we don't want heat to flow, or the insulating material that your oven is made of. So that way the rest of your house doesn't get to the temperature that's inside the oven. And all of these properties are going to depend on what is holding that solid together. All of these properties are based on kind of what is making this solid rigid in its own solid way. So we do want to spend a little bit of time talking about hardness. So you may have heard of something like the Mohs hardness scale, and you may have heard something along the lines of like diamond is the hardest material there is. But it's important to note that hardness does not mean strength. Diamond is not the strongest material out there because that's a hard thing to judge. There's a lot of different ways that we can characterize how strong a solid is, how rigid a solid is. Hardness means the resistance to scratching. So what this Mohs hardness scale tells you is literally the higher number will scratch the low. If you take two materials and you rub them against each other, you'll get a scratch on whatever has the lower hardness. So for example, if you take a piece of steel and you rub it up against a diamond, the diamond will not have any effect on it, whereas the steel would have a scratch. You'd be able to see the effect on there. So like your fingernail can scratch up talc, which is like chalk, but your fingernail cannot scratch a piece of fluorite because your fingernail is weaker. You wouldn't be able to kind of break pieces off of it. In much the same way that you don't expect you can scrape a piece of steel and have it show or anything like that. So that is really what hardness is about. There are other measures like toughness, which is a technical term, that measures how much something can kind of deform before it breaks, right? How tough a material is to break to cause to snap. One of the other things that come from these ideas of hardness, we think about diamond as being so hard. You think like, oh, diamonds are the best gems because they're going to be the best things around. But corundum, which is the type of mineral that rubies and sapphires are made out of, is also still very, very hard. And steel, like the most common hard thing you interact with, is much, much softer than corundum. You're not going to be scratching rubies and sapphire gems. So when there's a lot of marketing about diamonds are the only thing that lasts forever, just remember that that's really, your diamond isn't going to scratch. Don't worry, you'll see what can happen to diamonds later in this video. Hard solids tend to be more rigid. So things like ceramics. So ceramics is a technical term for types of solids. But the ceramic plates that you're used to are a type of ceramic. And so ceramics are really hard. They're really rigid. That's why we use them for things like dining plates, because they don't tend to bend. If you put a weight on them, they're going to stay still. But metals do tend to not be that rigid. If you've ever had like a metal cup or a metal bowl, they tend to get dings and dents in them if you've used them, especially like in like a camping context or outdoor usage. They have some wear and tear on them, and you'll see it. But they don't necessarily break, they just kind of get dents on them. Whereas ceramic plates do not get dings and dents in them. Instead, they just tend to shatter. So things that are very hard tend to, when they fail, when they break, fail and break in huge ways. So this is a piece of diamond being smashed by a hydraulic press. So highly recommend hydraulic press channel, very cathartic on YouTube. But so if you put enough pressure on the diamond, it will break and it will blow up like this, right? This is a huge shattering like a piece of glass. Glass is also a relatively hard material. It's hard to scratch glass, but you can see this sort of that when these hard materials do break, they just shatter. Hard materials are very good for grinding. So for something like, say, a drill bit, so these would be, you know, like for drilling, like for oil. So you'd have, you know, these drill bits that, you know, they are made of materials that are very hard, because you can see on this animation here, all they're doing is just rubbing up against the rock. So imagine if it's spinning really fast, it's like scratching the rocks a bunch of times. So you want something that is the hardest material that will break it up, that will rip up the rock that it's going through. And so it's commonly used, people use diamonds. So you get polycrystalline diamonds. You'll note that word. It means it's kind of flawed diamonds. Now that they're only flawed in the sense of like gem usage, but if in terms of if you want to be able to drill through any kind of rock, diamond is going to do it, right? It's that abrasion. It's just going to kind of rip out the rock, scrape it all away. And that's where you really need very hard materials for these sorts of grinding applications. So we can kind of tie some of these things back, these ideas about, you know, hardness, melting point, and conductivity. We're going to talk more about them in applications to particular solids. But one thing we can already say is that, you know, this idea of you had SiO2 crystalline was quartz, amorphous was glass. If you compare the properties of these two, the amorphous solid would have worse properties than the pure crystalline. So an amorphous solid will always be less hard. It will have a lower melting point and a lower conductivity. In this case, both of these are not conductive, but they'll always be worse. And it's because this is kind of the perfect crystal, right? This is the perfect arrangement. This is not. These atoms are not in the most ideal situation. So they're going to be able to break, right? The hardness isn't going to be that high. The melting isn't going to be that hard. And so you're going to have that issue. Another thing that comes from amorphous materials is because an amorphous material is just not ordered, they're all random. Every single amorphous material is going to have, you know, if you have all your glasses, you have a bunch of different pieces of glass, the atomic arrangements are all different. And so each piece of glass would have a different hardness and a different melting point. Now there's going to be ranges, you know, kind of relative ranges, but it's not going to be, you know, a clean like 100 degrees Celsius like you're used to for like, say, water boiling, or 0 degrees Celsius for ice melting. But it might be like, you know, glass melts at, you know, 1,000 Kelvin to 1,300 Kelvin, something like that, range of temperatures. That can be pretty substantial depending on how variable that amorphousness is. So we want to be able to kind of characterize and look at the properties of solids. In order to do that, we're going to need to talk about the types of solids, which we'll do in the next one. New topic with solids. Still looking for those participation 118 questions. See you in the next video.